Hello everyone, and welcome to my presentation titled ANN-Control System-Level Runtime Adaptable Approximate Computing, which we acronymed as ADAPT. I am Pratay Chowdhury, and I am a PhD student of Electrical Engineering at the University of Texas at Dallas. And this work has been done with the supervision of my PhD advisor, Dr. Benjamin Karim Schaefer, who is a faculty of the University of Texas at Dallas. At first, I will share a few words regarding the motivation of our work. We all know that low power is a very important VLSI design constraint, especially nowadays since all the designs are now run on battery, like smartphones and IoT devices and other edge devices. Use of heterogeneous system on chip or SoC is common to do complex tasks power efficiently. And heterogeneous SoCs contains hardware accelerator that executes specific tasks more efficiently and power efficiently than general purpose processors. To reduce power consumption even further, one orthogonal approach is approximate computing. So what is approximate computing? It means trading quality with area and power of a design. Why can we apply it? We can apply it to error-tolerant applications like image processing and DSP applications, because if we allow a certain percentage of error to them, a large area or power can be saved. Here is how it works. This is an example of standard Sobel edge detector. If we give an input image to Sobel detector, it will create the edge of the image. We will call it the golden output or the golden image. And if we use the input and all the internal data to train an approximation methodology, it will create several Sobel approximate designs. And these Sobel approximate designs will generate different output images from the same input images, and these images will have different qualities based on the quality metrics like PSNR or MAP. The challenge is to find the optimum design that leads to maximum area or power saving or energy saving within the given error threshold, because we will have an error target and we cannot exit further than that for approximation. Now we will look at how approximate computing works in heterogeneous SoCs. Modern SoCs are heterogeneous SoCs because they have different types of modules like memory, hardware accelerators, interfacings like UART and SPI on top of CPU or the processor, and of course a bus so that different modules can talk to each other. And these SoCs are not fully developed at behavioral level, because raising the abstraction level makes the design process much more faster. You design it on in behavioral language like System-C or C-like languages, and after high-level synthesis and logic synthesis and placement and routing, you will get the complete hardware design. And you can also run the portion of the application onto the CPU by compiling it and passing the instructions in the instruction memory and the data to the data memory. And each SoC component can be approximated differently, and the research work has gone on to see how these different methodologies work on different modules. And one way to do it is by reducing the supply voltage, because if you reduce the supply voltage, it will consume less power, but at the same time, it will induce delay, which will induce eventually error. So far, single component has been approximated as much as possible using different methodologies. And in our previous work, we have seen that we can achieve higher energy saving by mixing the approximations across the entire SoC. And we will, in this work, we will try to do so. And for this, we have proposed a controller that controls voltage across different modules of the SoC. We will call it the ADAPT controller. And here how it goes. In the picture of the SoC, you can see that we have just added an additional block, and this is our controller. It takes input from different stages of the SoC, and from the input during the runtime, it will calculate or measure the voltage needed to run different SoC modules and keeping the error within the threshold at the same time. And this is how we do the approximation. So our proposed flow has been that we developed has been divided into 3 phases. Phase 1 is to develop the behavioral SoC itself and create it, and we also do the errors versus VGD pre-characterization that will be needed for approximations. In phase 2, we will develop the ANN-based controller that will control the voltage of different SoC modules, and we will train it using from the simulation data we get from the previous phases. And in the last phase, on the third phase, we'll optimize the adapt controller to reduce its size, and we will convert the adapt controller module that is developed in behavioral level to a hardware description, so that actually high level synthesis can be done on it. So the phase 1, we will create the behavioral SoC first, and for this we will need the behavioral description of different phases. Different modules of the SoC, like the hardware accelerators, the processor, and the interfaces, and so on. And we have also developed our own bus generator that creates a synthesizable API. That means if you give the what type of bus you want to use, and what should be the arbiter type, and what should be the bit length, and so on, and what is the number of modules, like how many masters and slaves, and it will create the synthesizable API, and you just include the API to the behavioral description, and the whole SoC generation will be completed. And after that, the SoC is synthesized through high-level synthesis with the target frequency, and it will further synthesize up to gate level. And in this gate level, we will do simulation on it by giving it different types of input data distributions, or IDTs, because the data type in real world changes or may change. Like if you have an image on daylight, and the brightness of the image will change in the night. And we will save all the data, or store all the data, internal and also the input data, for our pre-characterization phase in the next part. And the SoC is simulated. After the simulation of the SoC with different IDDs, we'll do the pre-characterization of the gate level library. So we do it is that we simulate the library in spice level on different voltages, and get all the delay information, and create different SDF files for different voltages. And including this SDF file, we do the gate level simulation on different IDDs, and we'll get the error versus VDD exploration data. Now, phase 2 of our work is to develop the ANN controller. So we will need an optimal input size for that, and the input comes from different modules of the SoC, and we will use the simulation data we got from the previous phase to train our ANN structure, and the final product is that the ANN that can efficiently detect the voltage of different modules. So it will have the total number of output node it will have is the total number of modules. So, and we will also need to do a window exploration. So the window is the size of the input to the ANN, and we'll start from a minimum size to a maximum size. And it is obvious that if we increase the input size, the ANN can detect the necessary voltages much more accurately. And after the increment of the input size of the window size, the ANN accuracy will hit a maximum, and from there it comes into saturation. And the point at which it hits the maximum accuracy is our desired window size. So the data will be stored in this window or the buffer, and from the data, the ANN will measure or calculate the voltages needed to run the different SoC modules. And in phase 3, we'll optimize the adapt controller, like the truncating the weights and converting the floating points into fixed points. We can tune these parameters based on our need, and we can also prune away the smaller weight neurons. And after everything is done, we will have a much more decent ANN structure. And this model we can convert into a synthesizable system C description using HLS for ML open source framework. And after that, we will get a synthesizable C description of the ANN, which we will synthesize using an HLS tool and go down further into the path of hardware design. So we have so far we have developed our flow, and we want to try our design onto different kind SoC types to check whether how good our methodology works. And for that, we have used the following experimental setups. We have used Python TensorFlow to develop our ANN. For as HLS tool, we have used Cyber Workbench from NEC. And as logic synthesis tool, we have used Synopsys Design Compiler. And our target technology is the NAND gate open cell 45 nanometer technology. Our target synthesis frequency is 100 megahertz. And as power simulator, we have used Synopsys Prime Power, which is in general known as PTPX. RTL and gate level simulator, we have used Synopsys VCS. And spice level, for the spice level simulation, we have used Spice for Synopsys from Synopsys. And we have created 5 different SoCs using the hardware accelerator benchmarks we got from S2C bench. And we have used Sobel, FIR and decimation filter, and interpolation filter, and IDCT as hardware accelerator. And we have used MIPS processor as our CPU in the SoC, and we have run average of 8 benchmark on the CPU. And our bus, SoC bus is AMBA AHB bus. And here is the SoC configurations of the 5 SoCs we have developed. We have a CPU in all the SoCs and also the bus AMBA AHB bus. And we have a mix of different hardware accelerators, and every SoC has at least 2 hardware accelerators. Here is the summary of our experimental results in the table. And in the second column, we have the optimal window size for different SoCs. And in the third column, we have the exact power consumption of different SoCs on the workload. So our workload has 100,000 data, and it changes the data type arbitrarily into 200 different locations so that the IDDs are dynamic. And we also have the exact energy corresponding to the workload. And in the fifth column, we have the single average power of single approximation. So the single approximation is the approximation done on the largest component of the SoC. So it is our comparison benchmark. So this is traditionally what is done is that we approximate the largest component of the SoC to reduce the power. And for our case, we have approximated the CPU and reduces voltage. And in the sixth column is the power consumption when we are using our adapt controller, and it will change the voltage dynamically with the IDD. But in the case of single approximation, it has been approximated using the uniform random data type, and it has no controller on it. It has fixed voltage. And the next 2 columns have the average energy related to them. And in the last 2 columns, we have the average error of single approximations and also the average error of our adapt controller. And we can see that on average, our adapt controller saves 45% power compared to the standard SoC power consumption, and it saves 18% more power than the single component approximation of the traditional approximation methodology. And since the single component approximation is not designed to work on different IDDs, and so when our IDD changes, error increases, and we can see that it exceeds the error threshold set by us. And in our case, our error threshold we set was 10%. And on average, the single component approximation has an error of about 14 to 15%. So which is not accepted when we are approximating. And in our adapt controller, since it is dynamically adjusting the voltage based on the workload type, so it always keeps the error below the 10% target we have set. So in short, our methodology is very easy to implement because the availability of different Python ANN building tools we have PyCafe, PyTorch, and also the TensorFlow. And ANN is very easy to implement in hardware efficiently because a lot of research has been conducted on this front as well. And our method saves 45% power compared to the standard design and 18% more power or additional power compared to the single component approximation of the traditional approximation method. Our method successfully keeps the error below target, which is also another important factor while we are doing approximating. Thank you very much for listening to my presentation. Now I'll be happy to answer any of the question you may have. Thank you again.